everyone. Again, welcome back here. First of all, I decided to change a little bit the way. I was planning to do all the calculations about the second channel theorem today, but then I realized that it's too much math, and at some point you get lost and will not follow anymore. So I decided just to give you a bird's eye view on the proof, and I will upload by the weekend all the detailed calculation by handwriting in the website. But here we just put the main idea of the techniques that channel used to prove this theorem, which are important, and the consequences of the theorem, and then we will apply to a classical system. So we apply classical information theory to a physical system, and then we end up the classical part of the course, and on Monday we start the quantum part. We enter in quantum mechanics. So please raise your hands as soon as you have questions. Don't let the slides go on. Okay? So I think that's it. Yeah. Just, reviewing some stuff that we saw last Monday, because some of you could not be here. So just remember that we use these quantities today. This is just the joint channel entropy of the joint probability distribution of two random variables, x and y. Just extension of this extension of the channel entropy, which gives us the total uncertainty in both random variables. Okay, and this is a very important quantity. It's a central quantity in channel secondary theorem. It's conditional probability. It's how much the uncertainty in y decreases when I know x. So the Shannon secondary code theorem will rely on this quantity, basically. And the ideal case would be this guy equal to 0, which means that knowing x completely determines y. So okay, can you read the slides, no? Okay, that's nice. So that's conditional probability entropy, and then, as I mentioned last Monday, this guy is always positive, but in quantum mechanics it can be negative. So what we say today about Shannon, a classical capacity of channels doesn't hold in quantum mechanics. And these guys also extremely important here, which is the correlations between the two variables, x and y. So this guy is just the entropy, the joint entropy, with the negative sign, plus the average of this quantity here, which is the information that we would get if the variables were uncorrelated, were statistically independent. So I pick up the information that I get when the random variables are statistically independent, and subtract the information that I have when they are not, when I have the real distribution. So this gives me the total correlations between these two random variables, because it says how far I am from this guy, how far I am from independence. So this is actually very important. It is just the marginal distribution, the usual way to define these things. Okay. And this is extremely important quantity always, is the Kubeck-Leibler divergence, or sometimes it's called the distance, but not the real distance, but you can find this in literature. It gives you how easy or how hard it is for you to tell apart these two distributions of the same random variable. So that's why this thing appears in hypothesis testing and every communication scenario, because you have a random variable that you think that is P, but is truly Q. That's why the log of this guy here, if you break up this log in the sum of the log of this guy, plus the log of 1 over Qx, the log of 1 of Qx is the real information that you get when you measure the value of x, because the true probability distribution is but you think that you are taking average on these guys. So on average, you are wrong. This is telling you how wrong you are. And that quantity will appear today also. Of course, it can be infinite, but we discussed this last month. So let us go to try to describe the secondary channel theorem. Probably there will be typos here because I was working this during the week. But so if you see a typo, just let me know that I corrected that in the oh no. This is channel theorem. So we assume, as always, LSC wants to communicate to Bob reliably. What means reliably? Reliably means that LSC will send a message to Bob, and Bob is supposed to understand the message. So, but now we assume that the channel is noisy. What does this mean? I can talk to you now, and you understand. So we are using sound waves to communicate. So my voice is being codified in sound waves that your ears just decodify and you understand what I'm saying. But let us suppose that you have here an airplane with the engine turned on. It's too much noise. So if I keep talking, you will not understand because there is too much noise in the air. That's the kind of thing that channel deal. He asks the question if it's possible, even with noisy, to communicate reliably. That's the central question that he did. And once more, at that time, nobody thought that this would be possible. What would not be possible? To communicate reliably with a vanishing probability of error with a reasonable rate. So that's why this paper is so important, because channel proved, no, this is possible. So this is called the discrete channels two random variables. It will become clear because why we are using two random variables here in a bit. And the conditional probability appears here to characterize the channel. I will give an example in a bit so we understand why we have a conditional probability here and why this guy is so important. But intuitively speaking, if you don't know the message, then the input of the channel is simply a random variable. You treat it as a random variable because you don't know what's coming up. So the best description that you have is a random variable. And then you have noise, which changes this random variable, and the output of this thing is another random variable. So we call these X and Y, the two random variables. And the idea is it possible to reliably communicate with a vanishing, with a reasonable rate? It means that reliability means that this guy is close to zero. Oh, no, this guy is close to 1. The entropy is close to 0 because X is equal to Y. That's the idea. So if Y is completely determined by X, then there is no loss. That's why we model a channel as this guy here, as a conditional probability. And what's the capacity of the channel? The capacity of the channel is how correlated the two random variables are, these two random variables are. It means how can I learn about X, which is the input message, by learning Y, which is the output of the channel. So I want to maximize these quantities, the correlation between the input and the output of the channel. So I can determine X by measuring Y, it's in my hand. And since I know anything there, if I send you some message, these will be choosing according to some probability distribution, which is the probability distribution of the search. The maximum information that you can convey through that channel is maximizing these guys over all probability distributions. So that's not the proof, that's the idea why these things are the way they are. We are going to the proof in a bit. So, but let us give an example about what we're talking about here. Let us make a picture here. The probability of changing is P. So let us think that you have one bit of communication, because we're always talking about bit channels, which means that the channel, it doesn't matter what it is, it takes bits as input. So it's the most general thing that you can have. So Alice here wants to communicate to Bob, and then Alice sends a bit 0 to Bob and gets 0 or 1. The probability of unchanging is 1 minus P and P. Okay? The same thing happens with if Alice sends 1, which is 1 minus P, because the channel is symmetric. There are situations in this that here we have a different probability for different inputs. Yes, that is, but this is just an example. The general case, this doesn't have to be the same. But this is it's called a symmetric channel. And this is P of change. This is just a bit flip channel. So communicating through that thing, if a P is 1/2, for instance, it's completely random. You cannot communicate using a channel like this, because the flip, it will simply flip the bit. You understand nothing. Physical example of this thing: an optical fiber. An optical fiber does this. Let us suppose that you have an optical fiber here, and I want to communicate with this guy. An optical fiber is just think about it as a piece of glass. So we put a photon here, and the photon has polarization. So the polarization of the photon is the elicit of the electromagnetic wave is 1. So the polarization, we have 2 distinct polarization, which is horizontal or vertical, for instance. So we have if its polarization is age, we take 0. If polarization is vertical, we take 1. So that's a bit. That's a system bit. But what happens with the photon here? We input the photon into the channel, which is the optical fiber. It keeps deflecting here because of the changing in the refraction index. It will reflect like this. It will walk like this inside the optical fiber. But the problem is that we don't know the angle in which the photon is getting into the fiber. So this reflection is random because we don't know the angle. But we know from optical physics that reflection changes the polarization. So in each time it reflects, the polarization gets a random rotation. At the end, you completely lost the polarization, the initial polarization. So we need to correct these sort of things. So this is a physical implementation of this channel. One way, simple way to correct these things is error correction, which is this guy over here. Is a simple example of this. And it simply means, but this is the easiest way to do. So we have a probability of changing the bit. So we codify the bit 0 into 3 zeros. So the message is this one. This is the code word. Because of this, we are coding the message into the code word to get it input to the bit. The problem with this is that I can do the same thing with 1, and then Bobby gets 3 bits, and by majority vote, it decides if it's 0 or 1. Majority vote means that if he gets 2 zeros, then he assumes that Alice sends a 0. That's the way. The problem is that the probability of error of this thing, if you compute, this is the probability of getting an error, which means that flipping 2 bits. Because if it flips 2 bits, Bobby will decode the 0 as 1 with an error. So we need to avoid this. So what's the probability of error? It's the probability of flipping 2 bits. So it's the probability of flipping 3 bits plus the probability of flipping 2 bits times the probability of not flipping one of them. But we have 3 cases of this. We have flipping the first and the second, the third, the second and the third, and the first and the second. So 3 things that will give Bob the same error. That's why this 3 appears here. Okay. So this implies that this code will provide a probability smaller than P, which means that the probability of error will be smaller than this guy, than the channel, only for P in this interval, which is not good. It's actually very bad. But we can do this better. Yeah, we can. We can concatenate codes. That's error correction. I mean, in classical computation, we do this because we have a bunch of bits, so we can do this. But in quantum computation, we cannot do this because we don't have a bunch of bits this time. So error correction is a critical thing in quantum computation. So we just pick up any the 0 and starts like this. But any one of these 0 now is 3 bits. So if I want to transmit 0, this is not supposed to be a bar here. Sorry. Here is just a 0 because this is the message and this is the code word. So we have 90 zeros. If we compute the probability, so the probability goes to, in the same way you compute the probability of error, just counting the number of times that we have more flips than less flips. This goes to P to 4. And if you keep going, it goes to, it will increase, the next one will go to P, P to 6, to the power of 6. But so we can continue indefinitely, and you get a probability of error that goes to 0. What's the problem here? The problem here is what we call the communication capacity of the channel. If you have one of these guys, and if you have one of these guys with 0 bar, 0 bar, 0 bar, each 0 bar is 0, 0, 0. What's the problem here? The communication rate goes to 0. Can you see this? Because, I mean, if I want to communicate 0 in the first code, I need to use the channel 3 times. In the second, I need to use 9 times. And this goes forever. So the capacity of the channel is the number of bits that I communicate divided by the number of times that I have to use the channel. So that's the intuitive meaning of channel capacity. So channel capacity is a rate, which is the number of bits, divided by the number of times that I use it. No, let us put that. No. Number of times channel use. So that's intuitive meaning of a channel capacity, and that's why that's the quantity that we want to estimate. We want to pick up a finite number of these guys, but while going with the probability error going to 0. We want this. That was the question of the channel. That was the problem that Shannon attacked in his second theorem. The first one was just to comprise information to put as input of the channel. Now he wants to know how reliably he can transmit this information. So is that clear, the meaning of channel capacity and the meaning, or the problem is clear here? Is that okay? The problem that we're trying to understand. Okay. So that's nice. So that's the question. Is there a code? Is there a way to code information, noisy channel? Because if it's noiseless, then that is, you don't have to do nothing. While keeping a good rate of communication. It means this guy is finite, while this guy goes to 0. That's reliable. In 1948, nobody thought that this would be possible. because of these arguments here. I mean, no, you can communicate, but the information, the capacity of the capacity of the channel goes to zero. And this is extremely interesting because we can actually achieve this thing. A difference between classical and quantum channels that appears here, that you see later on, is that a curious thing. If I have two channels, two classical channels, whose capacity that we call C, both capacities are zero. So I cannot communicate through these channels. Like the example of the airplane that when you turn it on and I speak, then I keep speaking here, you understand nothing. So the capacity is zero. If I use both channels together to communicate, the capacity of the two channels will be zero. Because if I cannot communicate for this is zero. For the quantum case, this is not true. I can have two quantum channels with whose individual capacities are zero, but the joint capacity is bigger than zero. This is a problem, it's one of the most important problems in communication theory today. Nobody knows the answer. It's called the additivity. Classical channels are additivity, quantum channels are not. And nobody knows why, and nobody knows by how much you can break additivity. This is an open problem, one of the most important open problems in communication theory. And this also appears only in quantum mechanics. In classical physics, they are additive. So if I have a bunch of channels, I just sum up all of them, the capacity of all of them, and I have a total capacity. So let us see how we put the problem in mathematical terms. So what you have here, Alice, instead of 1 bit, she wants now to transmit a bunch of messages. She wants to communicate to Bobby and send a bunch of messages, and we take these messages from a set that we call M. And then there is an important assumption here that is uniform probability distribution of the message, which means that Alice selects the messages through uniform probability. If I communicate with someone, like I'm doing now, I'm not selecting my words according to uniform probability distribution. That's obvious. Otherwise, you understand nothing. But why do we assume this? Because you don't care about the content of the information that's being conveyed. We only care about the capacity to convey information. What is being conveyed, it doesn't matter. And I think that you are sitting there, I'm speaking here, but before I speak, you don't know what I will say. So you simply assume that you know nothing. And knowing nothing is uniform probability distribution. So Bob assumes that Alice selects the message from a box of messages, and this box has size m with uniform probability distribution. And input in the channel, and the idea is Bob to get the message and understand what Alice sent to him. Okay? Now we describe the channel as a conditional probability distribution because of this. Bob wants to know what's the probability of Alice putting a message and getting the same message here. Or in other words, Bob wants to minimize this guy, the probability of error. Because then he makes, if this guy goes to zero, Bob is sure that he got the message correctly. So the whole idea is giving the input, how the input determines the output. And that's why we describe the channel as a conditional probability distribution. Is that reasonable? Okay, that's nice. So that's the main thing. And the same thing that we did in the channel did in the other theorem says, no, let the channel send a bunch of messages. Each message is very huge. And then we treat everything as a pack. So asymptotic theory. And then we model the input of the channel as a random variable. Let us put it here. So we have the channel here, which is the input. That's the output, and this is calligraph key. This is the calligraph key, and we want to know these guys, x, y, which is determined by this guy here, which y given x. So we wanted this thing, while vanishing, but keeping finite communication rate, because I can reach reliably communication if I use the channel infinite times. But this is, is this correct? Okay. But we don't want to do this, and we assume the same thing. This assumption that we did the last time, they are the inputs of the channel are identically distributed and independent from each other, so we don't have correlations between the messages. We can have this that is called the correlated assisted channel capacity, or in quantum mechanics is entanglement assisted quantum capacity, which means that we increase the quantum capacity of the channel by using entanglement, by using correlations between the inputs. But this is a different thing. We can use this, but to create entanglement, to create correlations, we need to invest work. We need to invest resources. So these resources should be getting into account in the communication process. And in the same way, with the random variables are determined by these sequences here. This is also random variable because the sequence of inputs and outputs. And due to this hypothesis, it's easy to prove this thing. That is the same thing we did for the probability distribution on Monday. Okay. And then, as written there, the rate would be the number of message bits that I have, which is just the log of m, which is the size of the set that Alice has, the sense, divided by the number of channel uses. That's the usual way. So it's the log of m divided by n. And here we have a scheme that translates like this scheme here. So we have 0 is the message, with the m here, and we have the 0, 0, 0 here, which is the x, m, which is the code that we choose. Okay, why we are doing this? Because Shannon introduced a different thing in order to solve the problem. That's why we needed to select, to put this notation now, you see in a bit. So, given a certain code, we'll call C, which is, this is a code, but we have many different codes. So given a certain one, the probability of error, the average probability of error is just given by this expression, is the average probability of error in each message, given the code. Okay, this code, this is symmetric, but here I'm not assuming that's symmetric. It can be whatever. It's just uniform probability. This is a very important result that Shannon uses, because Shannon realized that what's the goal of the thing is to get a finite number here with this guy going to 0. So this guy should go to 0, while this guy is finite. That's the idea. But how do you bound this guy? It's extremely difficult to bound the probability. This is very, very difficult. But Shannon realized that that's easier to bound the average. And using Markov inequalities, if the average is bounded by some epsilon, there is a missing thing here, this epsilon is bounded between 0 and 1/2. Okay? It's important because otherwise this is not a probability. So if you can bound the average by Markov inequality, that I'll put in the notes there, you can bound the probability. So that was the idea of Shannon, for at least half of the messages. What does this mean? If I have two messages and I throw one of them away, then I lose half of my information. But if I have infinitely many messages and I throw half of them away, I lose nothing. That was Shannon realized it, and then he was able to bound this guy, and as a consequence to bound the maximum probability of error by throwing away half of the messages. That's the central idea behind Shannon's idea. And it looks like that is a bad thing, but the law of large numbers says that this is not a bad thing. I mean, when we get many very huge numbers, things are not not becoming intuitive anymore. But it really works, and we will see how it works now. So that's the content of Shannon theorem. It states that there is a code. It doesn't say which code it is, but there exists a code that achieves the capacity of the given noisy channel with a very small probability of error. That's the content of the theory. And there is one thing that I should say here is that, okay, Shannon uses this thing, but you can ask, oh, but I can use a distinctive set of codes or distinct set of probabilities. And if I use this, maybe it would be possible to get a better number than this. No, it's not, because Shannon proved it. Another one that's called the converse theorem, that it proves that this code is indeed optimal. So there is no way to get another one. The converse theorem is extremely more complicated to prove with very different techniques. I will not show it here because it's highly complicated, but if you want, I can put it in the handwritten notes. By the end of the course, I can put it there. But it's very different. The techniques are extremely different. It's a very different thing. Okay? That's why I'll not discuss, but I mean, believe me that this code is optimal. This is the best thing you can do. Okay.
So M is the set of all possible messages.
M is the set of all possible messages, yeah. What does, here. M, here. We have M messages. It's here, N. Oh, yeah, you're right. No, the length of each message is arbitrary. That's notation. That's notation, you're right. See here? That's the code. We abuse notation. So that, oh, yeah, that's true. Yeah, that's true. We have M, with the set here of messages. M messages. And we have X and M. As this message is, I mean, it can be whatever. This is the code word. So that's the size of the code word, which size N. Because then I need to use the channel to transmit this message. I need to use the channel N times.
M is the set of all possible messages.
Oh, it is. But the length of the message doesn't matter. I mean, this set has M elements, M messages. It can be whatever this number. And it can be a book. It can be whatever.
And this is the qualification of
Each one of these messages, yeah. M is one of the elements of the set M. Yeah. Well, I mean, I did this because otherwise I would have to introduce another set of random variables. And this is, I mean, it's getting confused. In the end, this guy doesn't depend on the message. Because we assume that we have a uniform probability distribution and we actually don't care about M, the small m. We only care about the reliability of communication. So that's, is this clear, the notation? I understand that it's too, I mean, it's too abstract, this thing, but, so this is the code word. That's code word. Associated with the message small m that belongs to this set. And this message, I mean, this can be one book, another book, it can be whatever. I just need to invent a code that translate all of that thing into bits that we input into the channel. Okay? Yeah.
And you said that this works in the infinite limit.
Yeah.
Of what? Of n.
Everything. I mean, the length of each message, this is finite, of course, but the length of each message should be very huge.
So n.
No.
N.
N should be infinite, go to infinite. That's the limit. That's the limit, which is called asymptotic limit. I mean, this is used in order for Shannon to employ the law of large numbers in order to prove the theorems. So that was Shannon realized that if he let this thing to be very infinite, he could bound average probability, and then using Markov inequality. Markov inequality just bounded the probability of a random variable to be smaller than the expectation value of the random variable, divided by a constant there. So he decided to pick up the random variable as the probability. That's the idea, Sharon. Which is brilliant, actually. And use this thing, since I can bound this guy implies that this probability, because if the average is bounded, then at least half of the messages are below this guy, this value. Okay? If the average is bounded, you have at least value. So you can prove this thing using Markov inequality. That's easy. And then the idea was, so I bounded this guy, throw away half of the messages that are above, whose probability of error are above this guy, this number, and that's okay, code just the other half. It looks like strange, but it's not. It's not, because of the law of large numbers. So law of large numbers of use of the channel. So which means this small n here goes to infinite, because this is counting the number of, this is this guy here, the number of times I use in the channel, with the number of bits that I can convey. And the thing that we saw last Monday, typical sequences and typical sets, here also holds the same thing, but now we have a new thing here, that just the typical set is not enough. Shannon needed to define the typical conditional set. We will see why in a bit. So beyond the typical set, he has to divide the typical set into a bunch of typical conditional sets to distinguish between the messages. But we will see this clear in a bit. And a new ingredient that was fundamental for Shannon to solve the problem. Otherwise, it was impossible to solve the problem. And this, he just say that Alice chooses a code randomly. But this seems, make no sense, because here, Alice picks up one of the messages randomly. That's okay, because she wants to transmit everything, so it doesn't matter how she picks up this message randomly, because I don't care about the content of the message, I just care about the reliability of communication. But once she chooses this thing, she needs to choose a code to codify the thing, and this code must be known to Bob, because Bob wants to decodify. What Shannon did here is that Alice chooses between a bunch of codes randomly. So each time Alice sends a message, she will use a different code. And this looks like, I mean, insane, because if I don't know which code Alice is using, Bob cannot decodify. And if Alice needs to send the code every time with the message, then it's meaningless, because you have to use another bunch of channels to send the code, so it's meaningless. But no, this is just technique. I mean, by doing this, he was able to bound the average probability. And then he removed these randomness and found and proved that there is one code, specific code, deterministic one, that achieves the channel capacity. That's the main idea. So that's was a clever choice by a clever insight by Shannon. Without this, I mean, we cannot solve the problem. Nobody was actually able to do this without putting these things or in the out of the syntactic limit. So, code words in this way, I choose in the random way, because you see, if the code if the code itself is random, then this guy is random. This xn is random. Is that okay? So this becomes a random variable. Here is deterministic variable, because given that this guy is random, but this is deterministic. Given that I have this, that's the only thing that can outcome. But here, no. Since the code is random, this guy is random. So everything is random. We have 3 layers of randomness in our problem. The first one is Alice's choice of the message. Well, the second one is the noise induced by the channel, which is random, because this guy occurs randomly. So we have these 2 randomness introduced in the system. The first one is determined by some probability distribution, which is uniform. The second is determined by the conditional probability distribution, characterized the channel. And now we have the third layer, which is characterized by the channel. The code, by the choice of the code. So we have 3 layers of randomness to prove this thing. And we are interested in these sort of things. I mean, also, everything is the same thing, identically distributed and independent. I mean, this means that Alice chooses a code, and this independent of the second choice and independent of the third, and all of them are choosing the same probability distribution. So, EHU. Then this implies that this probability is equal to this guy. I mean, yes, we did before. But this doesn't depend on M explicitly, because we don't care about what M is. This just depends on the probability that this occurs. Okay, so the code is a random variable, and the probability of choosing a particular code is this. So it's the probability of getting a message, and then the probability of choosing a code. That's the total probability of Alice to pick up a random code there. A particular code C0. Okay. Wow. All time is running faster. Okay. Then we have the average probability over the code distribution. So Shannon was computed. This is the expectation value of the average probability that we defined earlier. The average error probability, which is the average error that we have in over all the messages. That's the thing that we are interested in. But now taking over the codes is this guy, because this guy is linear. I mean, expectation value is linear, so we can simply write it in this way. And this is equal to this guy. Why? Because we don't care about the message. This is independent of the message itself. So I can pick up any number here. is going to be the same probability. It's going to be the same value. So that's the guy that we are interested in. So Shannon proceeded by computing the upper bound on this guy. That's the why using Markov inequality. So he was able to bound this guy, and by Markov inequality, he bounded the average probability of error, giving a specific code. So is that clear? Because of course, in the notes that I put there, all the calculations here will be explicitly given, but the idea should be clear here. That's the important thing. And then, so does anyone have any question? Nope. Is that okay? Okay. So this is the probability of error, the average probability of error of single code. That's bounded now. If this is bounded, he can bound the maximum probability. Why? There is, I found it this morning, there is a typo in the slides that's there. In the slide there is 1/2 here. But 2 is wrong. It's 1/n. Because the rate that you have, reducing the number of messages, the number of messages here is 2 to the n times r, where n is the number of times I use the channel, which is this guy here. And then is the number of messages log of this guy. So if I put log of this guy here, divided by n, this is just n, which is the size of the number of messages that I have, this m here. Okay, so remember that I told you that if you bounded the probability, if you bounded the average probability, then the probability is bounded. Half of them is bounded by 2 times epsilon. Half of the message, at least half of the messages. And then Shannon told, oh no, if half of the probabilities are bounded by this guy, then I simply throw away half of them, which is not bounded. So these are the number of messages. I divided this thing by 2. Then we get this thing. That's the reduced number of messages. But when n goes to infinite, this guy is very close to this guy. That's the idea. So the rate of communication is goes to a finite number, which is r, which is given by that guy here, and the maximum probability of error is this guy. So he was able to prove that the set of messages like this we can convey with this rate with eventually small probability. That's the main contribution of Shannon. But you see that throwing away half of the messages looks like too terrible, but it's not. In the asymptotic limit, this is okay. I mean, the rate, this is the new rate, converges to this guy easily. So that's amazing. That's how large numbers really work for us. So we want to keep a rate constant while taking asymptotic limit. That's the main idea. That enters now a second problem. Okay, we can convey information, but there is another problem. Bob needs to distinguish between the messages. Because, okay, Alice can send all of these messages with a finite rate and eventually probability of error. But Bob needs to distinguish between each of one of them. That's the second problem, decoding. Otherwise, it would not be possible to communicate. So we have this coded word. We need to identify the set of possible outputs of this coded word. Because you see, if Alice put a coded word that's x to n, and the output could be any one in the set of typical sequences, Bob would be unable to distinguish. Let me draw this thing. Oh, here. We saw in the last class that we have that's the typical the set of the input, and that's the I hate to draw this thing. That's the set of output sequences. Then we proved that there is a typical set here. That's the typical set that we call T, if I'm not mistaken. And the size of this typical set is P 2 to NHX. Okay? And then there is a typical set here, whose size is 2 to NY. But if I pick up a message here, XN, and it ends up anywhere here, then Bob is completely random to Bobby, because all of these messages here have exactly the same probability. This is the asymptotic equipartition property that you saw on Monday. So they need to pick up a code in which this set here is divided by conditional typical sets. What does this mean? This means that each one of these messages goes to only one of these sets. And these subsets of the typical set cannot overlap. That's the limitation. That's why we cannot communicate with an infinitely high rate. Because at some point, the number of typical sets here must be exactly the number of messages. That's the best you can do. So if I divide the size of the typical set by the number of messages, I have the maximum possible conditional typical sets. Otherwise, they will start overlapping and error will increase. Is that clear, the idea? That's why conditional probability enters here. Because this typical set is conditional to this guy. So that's why the asymptotic equipartition property should be proved also for the conditional probability. This means that I must be able to divide, there must be a code that enables me to divide the entire typical set into conditional typical sets, conditional in each message in the input. Okay, that's the idea of a conditional probability. So that's what I draw here. And well, the size of the entire set is this thing. So we are interested in this guy. And now you have the code, because the best you can do is just divide the number of typical sets, of sequencing the typical sets, divided by the number of possible conditional of messages. You have the number of conditional typical sets. And that is a thing that I'll prove there is a little bit different from the typical set, the typicality proved by Shannon entropy, but I mean the ideas are the same. I will prove they have the same property. Each conditional typical set has almost unity probability. What does this mean? This means that if I choose this guy here, when n goes to infinite, the probability of the output being this set goes to 1. Okay, so this is the first thing. Just remembering, if I pick up one guy here, the probability that this guy goes in this set is 1. That's the typicality that we saw now. Now is the probability that this guy goes to here goes to 1. It doesn't go to here or anywhere else, goes to here. That's the conditional typicality. It's stronger. And that's we needed to. And
but this is done by Alice choosing only a subset of possible codes.
No. They both of them can set. They needed to choose a code that does this. I will show in a bit how they do this.
But all the previous steps were assuming that you can uniformly Alice and Bob can choose the code words randomly, uniformly. Randomly.
But this was removed here. This was removed here. He just put the randomness in the code was used to bound this average value because we wanted this guy for a simple code. That's the problem. The average of these guys is completely useless for us because it's random code, so it means nothing. But by bounding this guy, Shannon was able to bound this guy. And that's the thing that you want to buy for a specific code. That's a problem. So the randomness in the code was removed here. So they have one code, but they don't know which code it is. But now they need to decide which code to use. And they must choose a code in which this is possible. Otherwise, Bob cannot distinguish between the messages. Is that clear? Okay, that's nice. So, and the size of the conditional set is this guy with the conditional entropy here. So this doesn't hold in quantum mechanics because this guy can be negative, so breaks everything down. This doesn't hold it there. And the same thing that you have there. Any conditional sequence, which means that if I choose this guy here, the output will be one of the sequences here with the unity probability, and each one of the sequences has the same probability. So if Bob just use the code, the knowledge of the code, because both of them must, but Alice and Bob must know two things. They must know the code, otherwise we cannot, communicate. Like the code here is English. If I start speaking Russian, it makes no sense because you don't know how to decode. So at least I think that you don't know how to decode. But and then he used the knowledge. The other thing is the probability, the conditional probability of the channel itself. But these can be characterized, like the example that I gave you with optical fiber. You make measurements and you characterize the level of noise that you have in that channel. This is experimentally done. They do this in quantum computers, they do this everywhere. So they must know these two things. Now they must, knowing these two things, they must fix a code in which these will happen. So use the knowledge of the code and see, oh, the messaging is in this subset. So Alice sent this messaging to me. So the communication works. That Alice generates this message according to some probability distribution, doesn't matter. Bob, of course, Bob doesn't know the messaging. He gets just the output with some probability distribution. Why? Because, he just knows the probability distribution of the messages that are getting there. So Bob verifies if this guy belongs to the typical set, one of these sets. He identifies which one the code belongs, the output belongs. So if yes belong to one of them, then first this big set, and then he used the knowledge of the code to identify in which one of them it does belong. And then the size of each one of these sets is this guy, which comes from the asymptotic equipartition property for the conditional probability. And now they did it just to structure the code. And how they do this? One is simply the number of messages that I want to send is this guy. It must be the size of the typical set. Why? Because any message that I pick up here will end up here, in some place here. So the size of this guy is this. And then I simply divide it by the size of each one of these sets. So what I pick up this set and divide it into equal numbers, which must be the number of the messages. Because if I have more messages here, they will start to overlap these sets. So the code must be, that's the best thing you can do. You cannot do anything better than this to communicate. That's related to the number of measurements, the number of messages that you have with the rate of the code. that you have. So this of course depends. Otherwise, I cannot distinguish between the messages. I cannot decode the thing. It's the same thing that we saw last Monday, in which I should, to comprise information, I should choose a code that can be decoded, uniquely decoded. That's the way we uniquely decoded this thing. And then, you know, this quantity, no? This quantity is just the one that I show in the second or third slide, is the information, is the mutual information. So that's the rate you can communicate. If I choose this code, this set of messages, I can communicate with this rate. That's the best thing we can do. I mean, if we put a number here that's bigger than this, what happens is that these small sets will start overlap and I cannot decode. So this is not reliable for communication. So that's the big picture that we have. And the number of these guys is limited by the number of the messages. That is no way to do better than this. And then, so we saw that the rate of communication must be smaller than these guys to be reliable, which is exactly the mutual information. But it doesn't matter. This probability distribution was chosen in a particular way by Alice. I mean, Alice was picking up messages in a particular probability distribution there, but this is not the capacity of the channel. If I choose one of these, this is the capacity of my communication scheme. The channel capacity is defined as the maximum possible rate of that channel. So we just maximize over all possible input probability distribution. And since we saw that this is mutual information is convex, it's concave, entropy is concave, there is a probability distribution that maximizes this guy. We know that there is one that maximizes this guy. And this is the definition of channel capacity. That's the maximum possible rate of communication that we have. Okay, questions? We end up with the first two channels. The first channel theorem told us what's the maximum rate at which you can compress information. And the second one completes the theory and said what's the maximum rate you can reliably convey information through a noisy channel. And this is the foundation of all we call today information theory. And of course, this is the converse theorem. We must prove that these codes are optimal, both of them. But they use extremely different techniques. It's not like these ones. You also can find this in the books. But the problem with the books is that these things, that's why I'm writing, handwriting notes for you, because the proof of this second theorem, for instance, it is spread all over the book. Because you need to prove a bunch of other things before to prove this thing. So it's spread over the first 14 chapters of the book. So that's why I'm doing just in one document, so it's easier for you to follow anything. It's much better. I don't know why they don't do this actually. But anyway. So that's the first part of today's lecture. Wow. Then I would like to show you an application of classical information theory to physical systems. So guys, welcome back. This is, I think that this was my first paper with my friend Mikko here. And as a direct application of classical information to classical systems. And the idea was to do it quantum mechanically, but we were unable to do because it's extremely complicated. So it's an open problem today. And then we realized that the classical problem was not solved, and then we solved the classical problem first. And the main idea is to describe a classical dynamical system as a communication system. and then to compute things that we want. So we need to translate between the language of classical physics to the language of communication theory that we were just discussing. That's the main idea. That's what the motivation of this work coming from this, because heat and work are especially well defined in classical physics, but in quantum mechanics we don't know how to do this. So we thought, oh, let us describe the system as a communication system. Then we define things there and translate back. That was the idea, but it's not that easy. Things turn out to be extremely different, extremely difficult, because there we can map the efficiency in information transmission, information processing, like the efficiency in transmitting information there, into work, and the inefficient doing this is losing information, so losing energy with heat. That's the idea behind this thing. So the main idea is to describe the dynamical system as a communication problem. Here, I will try to show how we did this. So first of all, some aspects of physics. There is a paper published by James, E.T. James, this paper here, 1957, in which he proved that equilibrium distribution maximizes information transfer. And from this principle, he derived all the statistical physics by using Shannon theory. That's amazing. It's a very beautiful paper. I don't know who of you doesn't have background in physics. I mean, everybody has an undergrad in physics. Okay, that's perfect. That's perfect. So the other thing is Landauer's principle. Landauer's principle is very important. Rolf Landauer was an engineer working in IBM, and he was interested in capacity of computation, and then he discovered a principle that logical irreversibility, which means that, for instance, erase information or any computation that takes more inputs than outputs, you cannot reverse this gauge. Not like eraser one. You pick several one and ends up in single one. Erasing a memory of a computer, for instance. This implies physical reversibility, which means that once you erase the memory of a computer, the temperature increases. There is no way to do this without increasing temperature. For classical systems like that one, this is meaningless because we are high above the Landauer principle, but for quantum computation, this starts becoming problematic. Because the energy that you generate is of the same order of magnitude of the energy of the system. So this is becoming complicated. You have to control this thing. This is reversibility. Linking physics with information. Now, today actually we think that physics can be seen as an information processing thing, as a huge quantum computer. For instance, John Prescott has a theory that the entire gravity, the universe, the entire universe is error correction. It's basically error correction. I mean, it's John Prescott. He can say these things, and he has a theory on this. But anyway, I mean, the universe keeps computing and correcting errors, so we are here. When the universe stops correcting errors, we die and everything is stabilized, and that's it. It's an interesting idea. But correct errors, we need resources. That's why we consume the resources. That's John Prescott's idea. It's a nice reading. Phase space dissipation. So this is if I have a classical process, and I take the system from one point to the other, doing something on the system, I perform the amount of work doubling on the guide, on average. That's the difference in free energy. That's the definition of dissipated work or entropy. And look who appears here. It's exactly the Kubel-Leiber divergence between the probability distribution of getting forward in time and the probability distribution of getting the process backwards in time. This is intuitively okay, because I mean this thing is saying that the entropy is just quantified by how well can you distinguish between a process occurring forward in time from the same process occurring backwards in time. If the system is reversible, you cannot distinguish between these things, and this guy is here and this guy is here. That's it. That's why it appears here. So it's a connection between information quantity and this guy, and thermodynamic quantity. Here is a different thing. This paper is also nice because it says that this is the amount of information that we need to predict the future with the knowledge of the present. So if I have a dynamical system, I need certain amount of information to predict the future of this guy. This is the memory of the system. It's how much information is codified into the system by the dynamics. So if this guy is positive, it means that we have anticipated work. Why? Because we're keeping track of useless information. And by Landauer principle, when you erase this guy, you generate heat and dissipation occurs. So this is a deep connection between information quantities and this guy. All of these holds for classical systems. These holds for quantum systems also, but here we have to replace this guy by the quantum relative entropy is a different thing. We'll see next week. The problem that we are interested in here is there any connection between randomness and dissipation. Randomness is like the output of a computer. I can think as if a bit string. And I can ask, how random is this bit string? And I just connect this with the efficiency of the information processing. And if the information process is not efficient, then we have dissipation. That's the idea link in this guy. So this is in this paper here. But the idea is very simple. We have a system that's in equilibrium state with a huge environment, with the inverse temperature beta. And then we isolate the system because we don't care about the environment anymore. And we let the system to go from the initial state to the final state under the action of a Hamiltonian. That can be time dependent. So it's a closed classical system evolving. Okay. Everyone here knows what phase space is? Okay, perfect. Nice. So, what you have in the theory, the Hamiltonian, with the state of the system at some time, and lambda is some external parameter that can be controlled. We have a set, it can be a set of external parameters, and we have the set of coordinates, which is the position momentum of with a point in phase space at every instant of time. We made an assumption that gamma is a finite dimension of phase space. It can be very, very large, but finite. Otherwise, the calculations don't apply very well. And the initial state of the system is just the equilibrium state, Boltzmann state, Gibbs state, with Boltzmann factor of probability. That's the usual thing. That's the theory that we are considering here. Since the system is closed, it evolves according to Hamilton's equation. So this Hamilton's equation generates a flux, which is phi. So phi just takes our system, the state of the system from one point in time to the other point in time, according to these guys here. That's the usual classical mechanics that we have. Gamma is a probability space. Gamma p is a probability space. So it's a probability distribution. If I measure p, p is a probability which is therefore a measure. So it's defined as a measure on this space. Here's the set of states that we have. So the Hamiltonian flow, that's phi, just takes our system to the initial state, to the final state, mapping the phase space into itself. And then we introduce the Shannon differential entropy. We solve Shannon entropy for discrete systems, but we can also define Shannon entropy for continuous probability distribution, which is the case here. That is just one thing, that this guy is defined with respect to some probability distribution. Because one thing that's nice in probability distribution that we need to take care is that there is no actually true probability distribution. What we have is a probability distribution conditional to some other one. So we need a reference to define probability distribution. And for discrete system, this doesn't matter. It means nothing there. But for continuous system, if you don't take care of this thing, then this guy can be negative, which makes no sense. So you need to define this thing with respect to some other probability distribution. Usually we pick up the uniform probability distribution as a reference one, which means that you know absolutely nothing. But it's always with respect to some probability distribution. It's just a technical detail when you go to continuous systems. Like you go from continuous vectors to discrete vector spaces, from discrete vector spaces to continuous vector spaces. Some technicalities appear there. But anyway, then communication system. Now we want to describe the system as a communication system, that system. How do we do this? To use the things that we learn from information theory. First, the source of communication system emits discrete symbols, as we saw in the last two lectures. It emits messages which are discrete symbols. That's the alphabet that we have there. And then there is an entropy here that we will define in a bit. Is basically the randomness of one of these bit strings, which called the Komarov-Sinai entropy. It is a measure of how random is each one of the sequences. And one interesting is that if I take the average when the message goes to infinite, of course, and the size of the message goes to infinite, when I take the average of this guy, which is defined for each one of the messages, I take the average of all the messages, what I get channel entropy, which is the entropy of the source, which is the randomness of the source. So this is a very nice quantity. And we want to define that's defined in algorithmic theory or information theory, communication theory. We want to define this for dynamical systems. That's why we need to describe the dynamical system as a communication system. So that's, first of all, we part into the phase space. This I need to draw. Otherwise, let us think that we have a phase space here. So that's gamma. And then I make some partition. Is that a different color? Oh, there. No, that doesn't work. Good. And then I make a partition of phase space. Here it can be whatever. It can be whatever. So I just made a coarse grain of the entropy of the thing. And each one of the partitions we name alpha. Okay? So alpha is an element of the partition. Let's call alpha belongs to A. A is one partition of the thing. Okay? So the partition is just a collection of these guys. All of them belongs to A, such that the union, the intersection of any one of them is 0, like we have here, and they sum up to the phase space. Okay, that's partition of the phase space. This is a coarse graining. It will become clear why we need to coarse grain here. Then we define another thing, which is refinement of the partition. I have this partition with this one, and then I apply our dynamical map once, which makes the entire phase space into the entire phase space. But it can map a point here, in a point here, or anywhere else. Because that depends on the dynamics. Where a point inside this element of the partition should be mapped, it depends on the dynamical system. It can even stay in the same partition. But let us, picture like this. It goes, this phase space, it goes to this phase space. this partition is mapped into this partition, which means that the points here were mapped in this way. No. Then we define this symbol here, which is the refinement, which simply define is the union, the intersection of this guy with this guy here, or this guy with this guy gives here, and we compute the intersection of these guys. So this is why it's called a refinement. Okay, we are refining the partitions. So this is defined by this symbol here. So this symbol means just refinement of partitions. So to do the map, we need to describe time as a discrete variable, because the message, the source of the communication channel emits messages in a discrete way. So I'll pick up every instant of time, it will emit a message. This guy, and it's discrete. This is not a serious restriction, because we can make elements of time as small as we please, actually. So this is not a restriction, actually. It's just for mathematical purposes. And then the evolution will be generated by interactions of this map, phi. So apply phi once, I have one step in time. Phi twice, 2 steps in time, and that goes there. So I define my alphabet as this guy, the elements of the partition. I mean, how the guy evolves. So these will be phi of A. So the guy, let us say that the guy comes a point here, comes here in the first moment, and then here in the second moment, and then here in the third moment. So if I apply this several times in several times, what I get is the trajectory of the system phase space. So each element of the message is a point in time of the trajectory of the phase space. That's the message. The message is the trajectory of phase space. Discretized. So we have our alphabet, which is simply the trajectory of the system phase space. And the source, which is the dynamical system, is just emitting these guys. Okay. So Kolmogorov-Sinai entropy, we can define for this guy, because if I treat this as a message, I can define that's it. I know information theory, I can define this thing. I just say it doesn't matter, as we saw in the last lecture, it doesn't matter who this guy is. It's a message. It's an element of the alphabet. I simply don't care who it is. But the problem is that to define this thing is highly complicated, or to compute is highly complicated because of this. To define is easy. So we define the coarse-grained channel entropy. Why? Because we can certainly ask, given the initial state of the system, what's the probability of the system to be in this particular partition? Or given at some time, what's the probability of being here? So we can certainly ask this probability distribution is well defined over the entire phase space. It's just the probability of at certain time the system is in the alpha element of some partition. And then we can actually certainly define channel entropy for this probability distribution, which is a sort of coarse-graining probability distribution. So we can do this. This is deeply linked actually with the Boltzmann entropy. If you compute this for Boltzmann equilibrium state, what you get is the volume law. It's the volume of the partitions here. So it's exactly Boltzmann entropy. That's why you need coarse graining actually. And then appears this guy, which is horrible, but it's nice. It's a nice guy. First, this minus n over here, this is time. Okay, but minus n is because of convenience. The system is Hamiltonian, so it's time reverse invariant. I can change the sign of the time and then I have the same thing because the evolution is Hamiltonian. That is micro reversibility. So we need to put minus here because of mathematical convenience to do the calculations. But you can simply forget this thing. Actually, I'm gonna take out this thing from the slides because it doesn't matter. It's just confused things, but it's the application is the refinement of the partition, like we did before here, but you do this over and over in time and compute the thing. And then you take the limit for time, it goes to infinite. And then this is easy to do. So this is defined for each trajectory. So this is the randomness of each trajectory that you have, or each bit strings that you have, each message. And you can think about this as an output of Turing machine. And you define this thing. Actually, this thing was defined there in that context. And you define this thing there is the randomness of the thing, and then you take the limit of time goes to infinite. You have a number, beautiful number there. But then this guy is extremely hard to compute. You have to compute the supremo of this quantity over all possible partitions. This is one of the partitions. I show in the slide another one that's split in two, is another one. But there are infinitely many partitions. So this quantity is beautiful, but extremely hard to compute. But there is a nice thing about this quantity, that for a system that fulfills Liouville theorem, which is amazing. Liouville theorem says that the measure in phase space, the evolution, the dynamical evolution preserves the measure in phase space, which implies volume is preserved. But it says that this guy is simply equal to this guy here, where lambda are the positive Lyapunov exponents of the system. This is a theorem. Do you know what Lyapunov exponent is? No, let us explain what Lyapunov exponent is. Let us think that I'm trying to predict the weather. The weather is a set of differential equations.
You can change to black piece because
Okay.
there.
Oh, sure. Okay. The weather is a set of differential equations, okay, like Newton's law, okay, and the problem is that they are chaotic. So this means that they have some parameters here, and I measure the parameters like pressure, atmospheric pressure, and other temperature and things like this, but these are not measured precisely well. I mean, we cannot measure these parameters infinitely well, with infinite precision. There are always some precision. So let us say that we have two solutions of this guy, but they're very close, initially very close. So we cannot distinguish between them. This is chaotic, which means that we have at least one, in this case the weather is just one, that lambda I, we have 3 in this case, but lambda I is bigger than 0. That's positive. This guy is Lyapunov exponents. They say that if I have a difference between these 2 points of size delta 0, this, roughly speaking, goes to this. So, if I have initially very close situations, very fast, they are completely different. They diverge exponentially. That's why you cannot predict weather for a long time, because it's chaotic. And these, if this is positive, if this is 0 for a pendulum, for instance, or harmonic oscillator, this is 0. So it's just oscillating. It doesn't change, never. So chaos is this. It means that highly sensitive to initial conditions. That's chaos. And that's the way we quantify chaos mathematically speaking. And what this is saying is that this guy, and this is a theorem, very nice theorem actually, is equal to the sum of the positive Lyapunov exponents. These we know how to compute. I mean, this is easy to compute. So we can compute this guy through this theorem. It's nice. It's very, very nice. We cannot, but this also says the meaning of this guy. This guy is a range because you see, this is exponential function, so this must be dimensionless. If this is time, this must be 1 over time. So this is a rate. Rate of what? Is the rate at which we are losing information. That's the meaning of this guy. Is the rate at which information is developing smaller and smaller structures in phase space. So it's harder and harder for us to get back the information. That's the meaning of this guy. So if this guy is positive, it means that the dynamic is trying to hide information from you with that rate. Yeah. Oh, yeah. The microphone.
Okay, so that expression with the Lyapunov exponents, it assumes a uniform distribution in the phase space initially, or does it?
This one?
Yeah,
No. It can be whatever.
it's independent of the.
It's absolutely independent. It only depends on the dynamics. You see, this guy doesn't depend on the initial condition.
But the entropy does, right? The entropy depends on the probability distribution that you are considering.
Oh yeah, but the probability distribution generated by the dynamics. That's the point. If I pick up let us think that I pick up a uniform distribution. So I have the probability of the system being any one of these things is are equal. Okay, and then I apply this thing, and I will follow one of the points. So this is one message, the trajectory of one of the points.
Yeah.
It's the same thing as I start with deterministic thing. You say that no, at initial time the system is here, but then the dynamics will let the system to other partitions, and this is the probability. This P alpha is the probability of the system to be in some element of the partition. So this depends on time also.
No,
Well, no,
not
not
getting
that.
it.
Well, see, what happens is we define the trajectory of the system, which is the initial condition. How did I call this? Just to not change the notation. Or that. We have the entire phase space. So it's the partition, this guy. And then we apply this guy to A again. This is the second point in time. And then we go. So this is t equals 0, t equals 1, and then goes away. That's the alphabet. In the language that we're using before, that's the alphabet
So
of our communication system.
Okay, I can think of the alphabet as labels for each of those time steps.
No, the alphabet is the trajectory for each one of the initial points. That's the alphabet.
Each of the trajectories.
It,
I label each of the trajectories.
no. That's important thing. How do we say we define a communication information source? We have the source here, which let us call X, and then it emits letters from an alphabet. So it emits, let us call A, or we call XM, XI, with sub-index I. So it emits X. And then we XJ, XK, and so on. And then it can emit again here at M, XL, and so on. So we have, these are the messages. The alphabet is here. And we have infinitely many messages. Because we are asymptotic. I mean, the source is just, keep emitting things.
Yeah.
So the letters of our alphabet here are these guys.
Yes. Okay.
Those are the letters.
Yes.
But note that here is a set.
Yes.
So we have a message. So each message is a trajectory.
Okay. Good.
And we have infinitely many trajectories. So
Okay.
that's the information. So the information source is the dynamics.
Okay, but what's the probability for each of those trajectories? What's the probability for a given trajectory? there?
I
Because
didn't
that's-
wrote,
that- that
I
probability.
didn't write this thing yet.
Okay.
This is just, the P of alpha is just the probability of the system, some system, to be in, it's just the probability of finding this point, which is the state of the system, at this element of some trajectory, of some partition. So I defined it here, the entropy of the partition, which is how coarse is this thing. If I decrease the size of these things, these probabilities converges to 1 or 0. And the system starts to become indeterministic, so uncertainty decreases. If I increase the size of the elements of the partitions, I get more uncertainty. That's the idea. So this guy is measuring how much information I'm losing because of the quartz grain. But the probability of one trajectory I didn't write yet. It will appear, but later. This is just how much information I'm losing.
Okay.
And then from this guy, I defined this guy here.
Okay.
And this is completely independent of the initial state of the system. The only thing that is here is, it depends on the partition, of course, that I choose, and depends on the dynamics. But then I compute the supremo of the partition. This guy only depends on the dynamics. And this thing is a different thing. This thing is a theorem. The guy that proved this called, I forgot the name of the guy. Okay, I think I have it here somewhere. But anyway, there is a theorem that proves that thing, which is independent of anything that I'm saying here. Is that okay? Did I answer your question?
Yeah, well, more or less. Let's
More or
see.
less.
Let's see if.
Okay. Yeah, that's not easy. That's not really easy to understand it. So that's why we map actually dynamical systems. We're mapping dynamical systems as messages into a communication system. That's the idea. Because I know how to define these for messages and not for dynamical systems. So now the probability of the trajectories. So the main result links how much information links this guy, which measures the randomness of the trajectories with dissipation, and thus with inefficiency of information processing. So that's the initial condition. Every initial condition generates a trajectory. So that's a message. You see, this means that the trajectory here is not the point at which the system is, but is a set of partitions that the system is. The set of elements of the partition where the system is. Okay, so that is a message, which is a trajectory of the system phase space, in coarse-grained phase space. Okay? Well, every trajectory, we can define a condition of coarse-grained probability density. That's what you were asking? That is the probability of getting the particle in element alpha t of the partition, given that it went through all these elements before. So this is the conditional coarse-grained probability density. It's a coarse-grained because it's a partition. I'm not asking where the system really is, but in which partition, in which element of the partition it is. So, and that's why you need to include distinguish the volume of the element of alpha of the partition. And then the idea is to compute the entropy of this guy. But the entropy of this guy, I don't know how to compute. It's extremely difficult, it's extremely hard. But we learned from Shannon that averages we can compute. So we compute average. But we cannot compute average also, but we can bound the average. So we compute the lower bound of this guy. That's the idea. And the rate, and then we link the rate at which this guy varies with Kolmogorov-Sinai entropy. And with this guy, with dissipation. So that's the main idea of the thing. And these guys are deeply linked. These guys linked with dissipation, like I showed to you, and we proved that this guy is linked to this guy, and this guy is linked to this guy. Then you link Kolmogorov-Sinai entropy with this guy through information theory. Is it now clear?
Sorry, I was trying to think.
No. Microphone. No, I know that this is. It took me a long time to understand this, and I'm one of the authors of the paper. So, it's really not easy to grasp this thing because we're mixing different things. But I'm not trying to. I don't want you to understand all the calculations. If you want to understand all the calculations, we can discuss, of course. We can go to the board and go through the calculations. But the idea, because the idea is important, because you can use this to solve other problems. Because one of the ways we have to solve a problem, especially information theory or quantum computation, or this thing, is to map one problem into another, that you know the solution. That's amazing. For instance, in Mike Wilde, he proved that if I give you a many-body Hamiltonian, and you can decide if it's gapless or not, which means that if you must decide if there is a gap between the fundamental and the first excited state, this problem is undecidable. How they proved this? By mapping this problem into the Haupt problem of quantum computation that we know that's undecidable. So this idea that I'm showing here, that's why I'm showing this thing here. This sort of thing is useful, mapping one dynamical system. We cannot, this was impossible to compute just using dynamical systems. But mapping through into communication theory, we are able to use the tool that you have there and to solve the problem. Unfortunately, quantum mechanically speaking, it's not possible to do. Because a very, very, very important thing that has to do with your question. Quantum mechanics, we don't have trajectories. So we cannot define Kolmogorov-Sinai entropy. That's the point. There is no Kolmogorov-Sinai entropy. Well, there are some proposals, but none of them are actually well accepted. So that's why we didn't do it yet for quantum mechanical systems. But okay, then there's the idea to link dissipation with randomness in the system, and randomness is we define it because we define it in terms of how random is a bit string emitted by some source. It doesn't matter which source it is. It really doesn't matter. That's the main result. It's just ugly, but it's the main result. It means this is the dissipated work, the average dissipated work. This is the usual thing that we have in thermodynamics. So this is the average energy of the system. This is the average free energy of the system. So this guy minus this guy is the entropy. It's just, the second law of thermodynamics says that this guy minus this guy is bigger than zero. That's the second law of thermodynamics, which means that this guy is bigger than this guy. So you cannot do more work in a system, perform more work in a system than you are able to get back from the system. That's the meaning of this thing, second law. But then appears this other guy here. This other guy here was the new thing. Is the information that you are losing because of the dynamics. So I'm not getting into the details, but this is this horrible thing here. So to compute these things are very hard. We can compute these, but these one are hard because these one depend on the partition, and then we must find the partition that defines Kolmogorov-Sennai entropy, and then use this partition to compute this guy. So this thing, we can compute Kolmogorov-Sennai entropy using this easily, but then we cannot compute these guys. So it's difficult, but it's possible to prove that these guys are positive, these guys are well defined. So what does this mean, actually? That's what really interesting. It says that if I keep track of the system, of each point of the system, so if I know everything about the system, every point, but with infinite precision, I know exactly where the system is and with velocity the system is. I know the point, exactly point in phase space the system is. Then I can follow everything. This guy is 0, and this guy would be equal to this guy. And that's it. There is no dissipation, there is nothing. Because I know everything about the system. I can compute everything. I can compute the future, the past, and everything. But I can't do this. This is quantifying the following. If I have finite precision in measurement to determine x and p, this means that this guy will be not a dot, but a certain area for me, a finite size, because I cannot, because of finite precision, I cannot tell if the point is here or here or here or here. I can only tell if it's here or here. But I cannot distinguish the points between, inside each one of these squares, okay? If the system is chaotic, this means that information is getting into the phase space and developing structures in smaller and smaller scales of the phase space, which means that I'm losing information because I cannot divide these structures smaller than these are. And I'm losing information exactly at this rate. These other guys is just to throw away the information that I lost because of the partition. So this quantifies only the information that I'm losing in time because of the dynamics. That's the thing. So this, in certain sense, it says, look, if you don't have infinite precision, you will lose information. If the dynamics is chaotic, there is no way to escape this. That's the point, unless you increase the imprecision that you are measuring things. And this is a precise relation between these things. The entropy produced due to the loss in the information due to the dynamics. And this was only possible because we know how to define this thing in communication systems. And now we know how to define it for dynamical systems. But for quantum systems, this is an open problem. How to extend this for quantum systems, I don't know. We thought that would be the same thing, but it's not, because we cannot define this guy for quantum systems. And then I don't know how to quantify randomness in the trajectories here. No, I mean, this is as the meaning of the things that we have. They're just explaining what I just told you. And of course, it's just the information generated by the dynamics. That's the thing that we want here. Of course, it's extremely hard. We were able to compute this thing for 2 extremely simple models. Because, yeah, actually, the first time we submit the paper was without any examples. Because, I mean, it's extremely hard to compute. But then they have no, look, compute at least one. And then we were able to compute, two very basic ones. But I even don't see too many physical applications of that thing, but anyway. But we know that if the system is chaotic, this guy is positive because of these, that I don't remember the name of this guy. This guy is positive, and we have an entropy production due to that will be generated by the dynamics. By the dynamics and by the fact that you are not able to measure it with infinite precision. So that's why I thought that to use this thing to solve the problem that we are studying with David. But I think that's true. It's more difficult. Yeah, it's more complicated. It's more complicated than this. So we provide new tools for study this thing. Is already? Oh, it's already known. Okay, but we are finishing. We are finishing. Of course, the quantum case, we don't know how to actually do this thing. We actually don't know. But this is this is a very nice application of information theory, and this can be applied to any. To any other problem. This sometimes is very useful for you to map one system to other that apparently are completely disconnected. You talk about dynamical evolution of classical systems and communication systems, but apparently they are the same. You can map one into the other, and then you can use the tools that you have in both to solve problems. This is very useful sometimes. So guys, that's it for today. On Monday we start the quantum part of this thing. So we enter the quantum theory of information. It's very, very nice. And questions, please. Of course, if someone wants to discuss, I'll be here. Just knock on my office there, and you can discuss the details of the calculations. And I need to correct 2 typos in the other slide that I will correct and upload again, and upload the calculations of the first part of today. The detailed calculations of the detailed proof of the second channel theorem. So you have them there.